Hi everyone, welcome to Selangor Human Resource Development Center or SHRDC. In short, what you guys are about to see next are a series of webinar sessions on various topics that we at SHRDC previously organized. We hope you will be able to enjoy and learn a couple of things from this webinar session today.
Hello and welcome everyone. I hope you guys can see me and hear me clearly. So please give me, please type in the comment box, in the chat box, if you guys can hear me, say yes or anything. Oh yeah, hello there, Umul, Fatima, thank you very much for commenting there. All right, thanks to Fatiha. So hello.
Hello, Muniz, are you there? Hello, Muniz? Hello, everyone. Good afternoon. Give us a second here while we look into some technical issues that might have occurred. Yeah, give me a moment. Hi, good afternoon, everybody. Thank you very much for joining this session here today. There is some technical issue on our side from the MC side, right? But I guess we can still continue with this session while we wait for the MC to join in. So, so good afternoon, everybody, for joining the webinar session on the data analytics, right? We have here today Dr. Rosaria. Dr. Rosaria, are you there?
I'm here.
All right. Okay. So a very good afternoon, everybody. And here we have today a very special guest, Dr. Rosaria, who is the KNIME's head of data science, who will actually share with us on the the Kickstart Your Journey to Codeless analytics. Right. KNIME is a very interesting and very unique platform, and it's also one of our Malaysian smart factory technology partners. Right. Who we work very closely with. Right. And here today, we have invited Dr. Rosaria to actually share with us on the KNIME platform and also some of the industry use cases that have been done using the KNIME platform and how it could actually kickstart your journey towards a codeless analytics. So without further ado, I would like to invite Dr. Rosaria to share her presentation on the KNIME technology platform. Dr. Rosaria? The floor is yours. Yeah.
Thank you for the invitation. I'm going to share my presentation.
Sure.
Okay, shall I start or?
Sure, Dr. Rosaria. Yeah, you can start. No problem.
Okay, so welcome everybody and thank you for the invitation. I feel very honored to be able to present at this webinar. So I was asked to present a series of case studies with some of the case studies I've worked on during my career. So first of all, who am I? I am Rosaria Silipo. I work as a data scientist or whatever it was called before since 1992. So I've been around for a long time. I am now the head of evangelism at KNIME. So when they ask me if I can present the case studies I worked on during my career, yeah, that's a lot of stuff. I've been around for more than 20 years. So obviously, I'm not going to present everything I've worked on. Just to give you an idea, more or less, of just a curiosity about the evolution of the field. So when I was not yet around, there were the expert systems, and they were placing the stress on the knowledge transfer from the expert to the machine. Then machine learning started around the 80s, and that's when I started my university, my college project. And here the stress was on learning. Then it became, at the end of the 90s, it became data mining, because the whole stress was about having enough data, having a lot of data. So all the databases, all the knowledge that you could extract from the data. And then, of course, since the data started growing and growing, it was called big data. The same field was called big data, using the big data technology. And then later, we had the data science, so that was combining the big data with the data mining, with the machine learning from before, and now we have the artificial intelligence. I would like to notice that when I started working on machine learning, it was also artificial intelligence. So I think I completed the whole cycle of the naming of the data analytics field. So how many of you know KNIME already? I don't know if I can see the answer here, but in any case, if you don't know KNIME, I'm going to give you a very quick overview on what KNIME is, the kind of software that we have, and why I think is special. Okay, so KNIME, with KNIME, we mean a lot of things. So we have the KNIME software and we have the KNIME company. The KNIME company is based in US offices in Europe and US. It stems very closely from universities and research. It's a spin-off from the University of Constance here, but it also, since it's open source, it benefits from contributions from different universities, including a lot of US universities. It has a global partners network. So as we heard before, we have a lot of partners also in Malaysia. The software is, we have actually two products. One is the KNIME Analytics platform, which is open source, and it's based on visual programming. So it's based on drag and drop, it's low code, it's not based on code. And then the other product is the KNIME server. The KNIME Analytics platform contains all the intelligence. So everything that has to do with the data. It takes your data from A to B, it gathers the data, wrangles, trains models, machine learning models, visualizes all this stuff. It's all open source, it's all free. The KNIME server is not open source. There is an annual fee, but it doesn't have the intelligence in the sense that it's only the part that builds the IT infrastructure. So once you have a model and you want to deploy it, manage it, consume it, optimize it. So basically, it's the commercial complement to the intelligence in KNIME Analytics platform. There is an annual fee because we think that the KNIME server is going to be used by companies rather than the KNIME Analytics platform, which is more used by the single developer, student, or data scientist, not necessarily integrated in a corporate environment. So the KNIME community, where can I find the KNIME community? We have, of course, a KNIME forum. You can find us on the usual suspect of the social media channels. We have every month, we come up with new verified components. I'm going to explain what the new verified components are. And then, of course, every month we elect a new contributor of the month, and we have a full hall of fame for the contributors of the month for the past 12 months. Okay. So again, we have two products. So the first, the KNIME Analytics platform is the product, the open source, a free product that allows you to create. And then the KNIME server is the non-free product that allows you to productionize whatever model you have been training. The KNIME Analytics platform comes with a core, and then, of course, it can be extended using the KNIME extensions, for example, the text processing extension, or integrations, for example, the Python integration, or communities, so not developed by KNIME, but externally developed extensions, like, for example, the image processing extensions, and even the partner extension. So there is a core, but this core is relatively small, but can be expanded using all of these extensions created by KNIME or by third-party people. So who are the KNIME users? Who does KNIME software address? I usually say, because people, they say, but then can I use it only for training a model? Can I use it only for collecting data? Well, so KNIME is a horizontal software. It addresses your data need from A to B, so from everything. If you are a business user, the business user is the one that you put in front of a web page, and he has the business knowledge. He can move a bit the data around, just a bit, some ETL, but absolutely no coding. If you're a business analyst, the business analysts are the ones who have the business knowledge. They shape the data, and usually they build reports. If you are a data engineer, so the data engineers are the ones with the deep understanding of the data architecture, and the ones who follow all the steps of the application into production. And of course, if you are a data scientist, that means that you are familiar with the machine learning algorithms and you want to apply them, and then with all the other data transformation. So for these four categories of data professionals, KNIME can be used by any of those, is used by any of those. And of course, all of them don't use the same features of KNIME, but they concentrate on special parts of the KNIME Analytics platform and KNIME server products. So for example, the data scientist will use the machine learning a lot, but for example, the business user, we will not, maybe they use the machine learning because it's integrated inside the application, but they don't want to know about the little details of the machine learning algorithms. So they use different aspects of the software, but the software addresses all of them. I already talked about the KNIME community. To go into more details, you can find help on the KNIME forum. There are a lot of groups on the KNIME forum. There is a journal, a Medium publication that we have just put out in June. It's called The Low Code for Advanced Data Science. And there we have a publication of different articles. I think we publish one article every 2 days. And the latest article, we have started that yesterday, is the 66 Days of Data Challenge. So I don't know if you know the 66 Days of Data Challenge. Basically, every day for 66 days, you dedicate 15 minutes, half an hour to learn something new. So we have started this roadmap yesterday, and we are going to guide whoever wants to follow us into this challenge for 66 days to learn more about KNIME, and this particular challenge is centered around data visualization. We are going to have other challenges later for machine learning, for example, or other things, but this one in particular is centered around data visualization. So if you want to participate, go onto the Low Code for Advanced Data Science journal on Medium, and then the articles that is now available is these articles for the 66 Days of Data Challenge. Again, the social media, you can find us there. There are tons of groups that you can organize by us or organize by the community. And then, of course, if you want to learn more about KNIME, you can check the self-paced courses on the KNIME side, and at the end you can be certified, and those are the badges that come with the certifications. We have 3 levels of certifications: basic, advanced, and the server level, so the production level, and then we have also a certification for the server administration. Okay, as I talked already about the contributors of the month, that's the Hall of Fame for the year 2021. You can find them here, and then another place where you can find a lot of material to learn more about KNIME is the KNIME TV channel on YouTube. The latest videos that we have produced on YouTube, they are the Data Science Pronto. They are small pills of data science questions and answers. So for example, do you know what the long short-term memory units are? We have a 3 minutes video that explains what they are. Do you know what how the gradient descent works, and so on. So all these very, very short video to explain, to answer 1 or 2 questions about some data science topic. If you want to know also what KNIME has been used already for, we have a page on the KNIME site. It's called KNIME Solutions, and you can see there are a bunch of different solutions implemented and hosted by a number of different companies. I'm not going to explain that too much. I usually don't do sales, so don't ask me too much about who's the customer and who's that, and so I don't know that. I know that these companies have developed solutions, and these solutions are available on our KNIME site. Okay, and then the last place where you can find a lot of prepackaged solutions ready to go, it's the KNIME Hub. The KNIME Hub is a repository of workflows. If you install KNIME Analytics platform and you open the KNIME Explorer, I'm going to show you where it is. There is a KNIME Hub, and that's the space that you automatically receive, private or public, where you can move some of your workflows. If you move them into the private space, of course, are visible only to you. If you move them into the public space, you are going, so all the other KNIME users can see them on the KNIME Hub. So you make them available for all the other KNIME users. We have a lot of workflows. So this is an old screenshot, but we have a lot of workflows. It says 4,000 workflows, but there is more. So it's likely that whatever you need to implement, some similar solution has already been implemented by somebody else and made available on the KNIME Hub. So remember, the KNIME Hub is a fantastic source of material that you can use. Okay, so those are the, again, the courses, and I'm not going to do that. Okay, so what can the KNIME software do? As I said, it addresses all your data needs from A to B, but let's go a bit more into details about what all your data needs are. So this is the most demonstrative workflows, is pretty useless, but it shows that it can do everything. It can do data access, including big data. It can, the yellow nodes are the nodes for data transformation. So they shape your data. For example, they perform an aggregation or a binning or a joining or a concatenation or a partitioning, or anyway, all the different string manipulation, all the different transformations. Those are all the ETL nodes, the yellow nodes. There are many. Usually when you see a workflow, it's a lot of yellow stuff, a bit of brown for the data access, a bit of green for the machine learning, and then it's a lot of yellow. So just to show you the importance of these yellow nodes, of the data transformation nodes. Then, of course, there is the whole statistics and the whole machine learning algorithms, and then the data visualization. The blue nodes are for data visualizations, and then, of course, there are a bunch of nodes for deployment, which means saving the model somewhere, building a report, or so whatever it is that you want to do with the processing of your data. So as I said before, the core of KNIME is not that big, but you can use a lot of different integrations and extensions. And the whole ecosystem of a KNIME Analytics platform, it makes it very, very powerful because it allows you to access a lot of external data sources. It allows you to access a lot of external AI, machine learning, deep learning libraries. For example, Keras for the deep learning libraries. We have a bunch of nodes built on top of Keras that, of course, allow us to perform the same deep learning as in Python, but using the Keras libraries, but from using visual programming without coding. We have the Python. You can use all the Python through the Python integration. You can use all the Python machine learning libraries, DR, and so on. We have a bunch of integration with reporting tools and visualization tools like Tableau, Power BI, Plotly, and so on and so on. Scripting languages, and then all the distributed and cloud executions. So, for example, you can access the Google Cloud, run your workflow on Databricks, on Cloudera, on Azure, on AWS, on Redshift, and so on. So we have a number of integrations with different data sources, technologies, and libraries that make KNIME extremely, extremely powerful. To describe a few years ago, to describe this capability of KNIME to access many different resources, including external libraries and including external scripting languages, and especially external data repositories, we started a series of blog posts that was called Will They Blend? The whole blog post series was that we take one data from one data source and then data from another data source, the weirder the better, and then we would show them how to combine them together, usually via concatenation or via a joining node. This series of blog posts has been collected together in a book, and this book is the Will They Blend book. It's a free book. You can download it. There are short stories of blending data. So you can find, for example, how we blended together the images from a Romeo and Juliet performance with the text coming from an EPUB document of Romeo and Juliet. And then we combined, we built the graph of who was talking to whom in the tragedy. And then this graph was populated, the nodes of the graph representing the characters of the tragedy was populated with the images of the characters of the actors in the theater performance. So there are all these different stories. They're easy, but they show how they are easy because it's easy with KNIME to access different data sources. So they show how powerful KNIME can be just to access the data. And if I've been around for a long time, and before we had KNIME, we had to do really a lot of work to be able to access, for example, a PDF document, or to extract the content from a PDF document or from a PowerPoint document. Or so it was only easy to access the tabular data. With KNIME, it's much easier to access all kinds of data. Okay, so let's see how KNIME works. This is a little video. So here is the KNIME Explorer. If you see up here, there is the My KNIME Hub. The My KNIME Hub is this space that you automatically receive when you install KNIME. You receive to host your projects externally to your computer. You can have, again, a private space. You can have a public space. The public space, of course, is public. Everybody can see the work. Here you have the list of nodes, and here you have a recommendation engine for what's the most likely node to come in your workflow. And this is the workflow editor. That's where you build the workflow. So it's you just double click or drag and drop nodes from the node repository into the workflow editor, and then you build this pipeline of nodes. So first you read the node, then you join the node, First you read the data, then you join the data, then you transform the data if you need any kind of transformation, and then, for example, you partition them, training set, test set, you train the model, in this case it's a decision tree. You train the model on the training set, you apply the model on the test set, and then eventually you apply a node for scoring the performances of the model on the test set. So this is the last node. So here you build an ROC curve, and this is the scorer node for the scoring. Every time you select a node, here you have the description of what the node does and what the settings of the node are. So whatever parameters it requires to work. And yeah, so that's all here. This is the visual programming philosophy, so that you drag and drop blocks, nodes in this case, that are specialized, dedicated to do something, and then building this pipeline, which is called workflow, you are able to bring your data from A to B. Okay. Again, so this is the workflow that we built before. Again, accessing data, yellow data for transformation. In this case, there is this partitioning. You have the training set on the top branch, the test set on the lower branch. You train the decision tree on the training set. You apply the model on the test set, and then eventually you apply an ROC curve or a scorer node to quantify the performance quality of the model. Each block is dedicated into doing something, and it's called node. A pipeline of nodes is a workflow. Notice that under each block, each node, you have this little traffic light. The traffic light represents the status of the node. Red means that it has been just created. It's not ready to do anything. It has to be configured. Then if you configure, that means you put the right settings. For example, if it's a decision tree, you want at least to define the target variable that the decision tree is supposed to learn. After it has been configured, and it has been configured successfully, then the traffic light becomes yellow, and then if it's executed and it's executed successfully, it becomes green. There is a fourth state, which is the error, which appears when there is an issue with the execution of the node. Okay, you can also create new nodes. You can develop new nodes, of course, if you are a Java developer, but if you are not a Java developer, you can just select a group of nodes, then right-click, and then create a component out of this node. This is a component, this gray node that appeared here before. The component contains the node that you have selected and put into the component, which means that the component is at all effects is a new node. You can, there are even nodes that can build a configuration window for the components, and nodes that can build a graphical view for the components. So the components can become a node made of other nodes, but a new node. And the new node can be also quite flexible and powerful, complex, depending on the sub workflow that you build inside the component. So the component have become quite an important part of KNIME, because they allow you to customize your node repository and abstract some logic blocks into a new node. Some of these components, you can find them, they are available anyway. I'm not going to talk much about the components, but you can find them, because some of them we build, some of them people build, and some of them they get verified. The ones who get verified, then they become available to everybody, and they are somehow certified by KNIME. Okay, so let's see, this is what KNIME Analytics platform does. So far, we are in the field of the open source and free. So let's see what the KNIME server does. The KNIME server is, as I said, there is no intelligence. So all the machine learning and statistics is in the KNIME Analytics platform. There is no lower version and a higher version. It's all in the KNIME Analytics platform. What the KNIME server does allows groups of people to collaborate together, allows for automation. So that means that you can schedule and run remotely different workflows for different orchestrations of tasks. allows you to deploy either as a to deploy your solution as either as a web service or as a web-based application. We call them guided analytics application. And then, of course, it has different level of securities. So it allows you to hide things. It allows you to anonymize things. So it allows you a level of security, especially against errors and some disasters that can strike that the KNIME Analytics platform doesn't do. Okay. Okay, so if you want to know more here, there are a few more slides about what the kind of applications that you can build to run on the KNIME server. They can be completely web-based, so you can have a step-by-step web-guided application. You can build dashboards, you can build a number of things as interactive as you want. So it's very flexible, but I'm not going to describe that much here because I have a long presentation and there is no time. And then, of course, you can also decide how scalable your execution can be. So you can use many different executors in parallel. Of course, you can parallelize the execution, and then you can also decide each executor where it's going to run. If it's going to run locally, if it's going to run on the cloud, for example, if it's going to run on a database, if it's going to run on a big data platform, if it's going to use the GPU, if it's, I don't know. So all these different options to make the execution of your application more scalable. And a lot of these options are not available in Analytics platform, they're available only in the server. Okay. Any questions on that for now? I see that there is a... Okay, so there is the poll question that Marisa should run the poll question now.
Yes. Hi, everyone. So sorry if earlier on there was a technical issue. Sorry, Dr. Rosaria and other participants. So before Dr. Rosaria move on with her next topic or slide, we will release a poll questions shortly. So just give me a second.
So in one of the questions, there was somebody noticed that there was Weka among the integrations of KNIME. Of course, there is Weka, there is also R, there is also Python. I mean, we integrate practically with everything besides, of course, everything that is open source, besides, of course, the solutions that you have to pay for. Okay.
All right, everyone. So you should be seeing the poll questions on your screen. So we would greatly appreciate if you guys can answer this. It's only 4 questions, so we can know where you guys are coming from. Okay, and what are you guys looking for, or your expectations from this webinar? So do answer the poll questions that you guys are seeing on your screen. All right. Meanwhile, this poll we will run it for a few minutes. So Dr. Rosaria, you may continue while this poll is running. Okay. So you may proceed to talk.
I'm checking the answers. Great. So there are some people, they know KNIME already. That's nice to hear. I used to present KNIME and nobody had an idea. That was a few years ago.
Mm-hmm.
Okay.
Meanwhile, Dr. Rosaria, we do have a question from Nurul Hazali. She is asking, will you be sharing the slide presentation?
Yeah, sure, of course. After this presentation, I'm going to send the PDF to Marisa, and then she's going to distribute that to the attendees.
All right. Thank you.
Okay.
All right. You may continue, Dr. Rosaria, if you like.
Okay. Okay. So then let's start with the case studies. So what I have implemented using KNIME through all my years at KNIME. Now I've been at KNIME almost 7 years, so in these last 7 years. Okay, let's have a look. So as I said, I've been around a long time. So I have worked on a lot of different topics. Of course, the classic is in accounting and banking. So all the risk assessment, all these, the prediction, if I want a loan, if the machine is going to predict if I am going to give back the money of the loan or not, and these kind of things. And then another classic is the customer intelligence. The churn prediction is the thing that everybody that I know has to do. Everybody has customers. Everybody wants to know if their customers are going to leave or not. So churn prediction, customer segmentation to a lower extent are also the super common, easy. They've been around for 30 years now, applications that people can put together. And then there are some new ones. In the 2000s, the recommendation engines came out. I developed two different applications, one using the market basket analysis with the a priori algorithm for a supermarket chain. And the other one is the classic movie recommendation using the collaborative filtering on Spark. Social media analysis, then of course there are medicine case studies, and then of course the latest is the IoT. Cybersecurity, and then there is the whole deep fake. So here we played a bit. I think I find the deep fake. How can I say? So it's nice because it allows you to move the barrier of the machine learning, the artificial intelligence, but at the same time it's still a gray zone because they say that if you generate a fake face, then you can use it in, for example, in marketing, but I wouldn't be that sure. So I don't know, maybe we should talk to a lawyer before we start doing these kind of things. Anyway, for the deepfake generation, we have created text in specific language in the Shakespeare style. We have created new rap songs, new product names. Now the latest article is creates music. The model has been trained on Schubert's music, and it creates music that is Schubert style like. We create fashion, new fashion. We create, of course, the cats and dogs. They have to be everywhere when you talk about deep learning. And then we did also an application on image restyling. So I can't present all of them today. So I've chosen only some of them. Of course, I had to put in there the churn prediction because that's the easiest thing to explain. Yeah, and I'm going to explain a bit also about the accounting and banking because that's another area that it's relatively easy, but it can be automated a lot. And then I'm going to talk about the Internet of Things, some application for the Internet of Things, something about cybersecurity, and if there is time, I'm going to talk about some social media analysis. So that means NLP, sentiment analysis, and topic detection mainly. Okay. So you know this figure, this is the CRISP DM cycle. So now the CRISP DM cycle is only one part, is the creation cycle of a machine learning model. Of course, we are in this presentation, I'm going to focus on the creation cycle, but then of course there is this whole part about validating the model, making it, moving it into production. So deploying the model, monitoring what the model is doing, updating, retriggering the training if necessary, and then of course making it available to all end users without them knowing what's running inside the application. But anyway, for today, I'm going to concentrate in the creation part of the model. And if you want to know more about the production part of the application, we can discuss that later. Okay, so let me see if there are questions here. Electrical power system. Yes, absolutely. I'm going to show something in the IoT part about electrical power systems. Okay, so let's start with the customer intelligence and finance and banking. The easiest, that was my first project when I started using KNIME, is the calculation, ARR calculation, annual recurring revenues. This is a relatively easy task. There is no machine learning involved. We are not supposed to predict anything. We are just supposed to aggregate things. We have a bunch of contracts, and then based on these contracts, we are supposed to aggregate the value. And then we are going to have a time-based plot that is going to tell us how much the annual recurring revenue is, the total annual recurring revenue is for each month of the year. So it's a purely data transformation aggregation exercise. And still, so as far as I know, in a lot of banks, they still use Excel to do that, right? And Excel has a few issues. The biggest issue is that there is no error check. So if you make a mistake, you will never realize that. So that's why maybe making it automatic and using KNIME, it's an easy automation of a relatively easy task. So this is the workflow that I put together to build and visualize the annual recurring revenues. We read the data, right? The data is stored in Excel sheets. Of course, it could be stored also in a database. Here, it was stored in an Excel sheet. This is the component. You remember I told you that the components are nodes with inside other nodes, and those are nodes that I create, right? So actually I didn't create this one, a colleague of mine did, but I just took her component. You see there is this green arrow here. That means that this is just a link to the original template of the component. So I took her component, I drag and dropped it into my workflow. It was working fine, so why do I have to reinvent things? And so I reused her component here. The linking character of this component to the template, my colleague is the owner of the template. If she develops a new version of this component, it's going to end up in the template. And then when I open my workflow, I'm going to get a message, there is a new release of the component, do you want to update? And that's the whole character of this link, the link character of this component. Then I do a bit of transformation, not too much, which mainly it's a group by. The group by is the node that does all the aggregations. It's a beautiful, beautiful, beautiful node because it allows you to do all sorts of aggregation, counting, percent, all sorts of operations on the data set. So here I calculate the sum of the values by year and by month to calculate these recurring revenues by month. And then, of course, I do some more aggregation, and then I perform the visualization of the annual recurring revenue. And those are the plots, right? So here I have the month, and then you can see that I compare the 2015, 2016, 17, and so on in the annual recurring revenue page, and I perform the same also using the line plots. Yeah, so this is the two representations. Basically, it's a dashboard. This is just a screenshot, but here there are some buttons that allow you to make the dashboard interactive. So you can, for example, select one bar, and then the corresponding data is going to be selected in the other plot. Okay, so this was an easy application. It allows you to automate a relatively easy task and make it more error-proof. Let's talk now about the other classic application. Any example of case relating to Islamic social finance? No, I don't have that. I don't have that. Okay. So let's talk about customer intelligence. So the other classic example is the churn prediction. I always show this one because it's for the ones who don't know how the data science cycle works. It's a perfect, easy example to describe the data science cycle. So you know what the churn prediction problem is, right? So we have a CRM system, and we have in the CRM system, we have data about our customers. The data are usually three types of data: demographics, so all the demographics about the customer; revenues, so how much money, how many contracts, and how much money has the customer contributed to the company; and then, of course, behavior. So this is the more complicated part to define the behavior because it depends on the business and it depends also on the data. But for example, the loyalty is a classic measure to measure the behavior of a customer. And then the churn prediction is based on these data, demographics, behavior, and revenues. From the past, I have a data set from the past, and I know that some customers have quit the company, they've moved to the competition, and some customers have remained with the company. So I want to be able to analyze new customers and say which customer have a high likelihood of churning, so to leave the company and go to the competition, and which customers have a lower likelihood of churning, because of course I'm going to treat them differently, right? I'm going to analyze if there is a problem in the ones who have a high likelihood of churning. Okay, so let's have a look at how the workflow is done here. Again, there is a part of data reading. In this case, it's again an Excel reader and a file reader. That's because I take the, actually the original data was in a database from the CRM system, but of course I had to take this data. It was a fake data set. I had to take it around for demo, and I moved everything into a CSV file and an Excel reader, an Excel file. So then the data, one data set shows the operational data. So this was a telco data, and the operational data showed basically how many calls they were doing in different times of the day. And then the other data set was about the contracts. So I joined them together based on the ID of the customer. I transformed a few things into string because my decision tree learner needs a target variable, which is a string variable. I added some colors because colors are always nice, but absolutely not necessary. And then, of course, I partitioned the data, training set and test set. You know that the machine learning algorithm has to be trained on the training set and then evaluated on the test set. So I trained the decision tree learner on the training set and I applied it on the test set. And then again, I have an ROC curve and a scorer node to evaluate the performance of the model based on the test set. So here I used an equal size sampling because the data set had a large imbalance among the classes. Of course, the customers who in the past churned were much less than the customers who remained. So the imbalance between the two classes was noticeable. While the decision tree is not that sensitive to class imbalance, the testing should be helped a bit because the overall accuracy is not a good measure of a data set with strong imbalance, class imbalance. So in this case, we use the equal size sampling to reduce the two classes to have the same size and then to force the overall accuracy to take into account the performance on both classes. This is because at that time, that was my first or second application that I developed with KNIME. At that time, the scorer node did not have the Cohen's kappa measure. If you know a bit about scoring measures, you know that the overall accuracy just makes an average of all correct and not correct predictions, which means it's influenced by the a priori probability of the most numerous class. On the opposite, the Cohen's kappa makes the makes a similar measure of the performance of the model on both classes, but takes into account the a priori the a priori probability of the two classes. Anyway, at that time we didn't have the Cohen's kappa in the scorer node, and that's why we use the equal size sampling. Now it's not necessary anymore. Now I've trained my model. I have saved my model. In this case, it's a decision tree. But then what I really want is that I want to score my new customers to make sure that they are always happy and they are not at risk of churning. So in this case, we abandon the training workflow. We save the model somewhere using a model writer. And then we build a new application, which is the deployment workflow, the deployment application. The deployment application takes the new data, takes the model that I have trained, applies the model on the new data, and then it gives to the end user some measure of the probability of churning. And that's what this tiny workflow does. Reads the data, reads the model, applies the model to the data, performs some preparation of the data for a nice visualization, and then, of course, it performs the visualization here. And that's the visualization. You can see here that you have a list of customers. Those are the new customers, the ones that I analyzed today. There are 5. And then you can see that the orange one is the probability of churning. And then this one, for example, has a higher probability, same probability of churning than of not churning. So it would be nice to check what the problem with this guy is. Here I have a tile view with the details of my customer. I can check the tile, and then I can I can check the customer in the bar chart, and then the tile pops up with the details information of my customer. And then I can see, for example, that he has called many times the customer, the call center, and he didn't get any answer, and he's getting more and more upset, something like that. Okay. Okay. I'm going to check the polls later, or shall I check it now?
Okay. Later is fine, no worries.
Okay. Of course, when I implement, that was my first implementation, as I said, for the churn predictor. And as I showed you before, I used an Excel reader and I used a CSV reader. But then, of course, a more professional implementation would be to access a database, perform some of the data extraction and data transformation on the database, because it's faster, and then eventually extract the data from the database. Another possibility is that instead of just showing one dashboard at the end, I could show many different steps. So for example, here I can ask, I can start my application from the KNIME web portal on the server. I insert for example, the password, the username and password to access the database. Then I perform some kind of visualization of the original data set. And then finally, I can isolate some of the customers based, for example, on the likelihood of churning. And this is another one of these web-based step application. Okay. Next is the risk assessment. So what we have learned from these small examples of churn prediction is that reading data, transforming data, partitioning data into training set and test set, training the model, the machine learning model on the training set, evaluating that on the test set. And this is true for most of the applications involving supervised learning, machine learning algorithms. So for example, the next application is the risk assessment in banking. Here we have a customer history, and then based on the customer history, we want the model to generate a risk prognosis. So the probability that this person who's asking a loan now is going to give back the loan at some point. So we have people that are low risk, so they are reliable, people who are medium risk, very low risk, high risk, very high risk, and then of course, depending on the strategy of the bank, we might not want to grant the loan to some of these very high risk people, for example. Well, we can discuss that, but let's suppose that we don't want to grant the loan to some of these very high risk people. So here the data set was the history, the delinquency history of some of the customers. So if people have been, for example, in jail, if they haven't paid loans before, so if they have a history of criminal behavior. And that's the workflow. Do you notice the workflow is exactly the same as the other workflow? It's very similar to the other workflow. So again, I have a training set and I have a test set. In this case, I don't join, but I concatenate because they are different. And then we perform some data transformation. We calculate some linear correlation, and then again, we split the data set into training set and into test set. We apply, we train a machine learning model. In this case, it's a random forest, before was a decision tree, to the training set. We apply the trained model onto the test set, and then we evaluate it using some of the performance metrics calculated by the scorer node. So it's exactly the same. It's always a lot of these applications using supervised machine learning algorithms, so they work the same. You read the data, you transform the data, maybe you do some visualization, some exploration like the linear correlation, then you separate into training set and test set, train the model, test the model, and then you have some measure of how reliable your model is. In this particular problem, we also had unbalanced classes. So before we had the decision tree. The decision tree is not doesn't depend on that is not influenced by the a priori probability of the data set classes. Actually, the random forest neither, because the random forest is an aggregation of different decision trees. But another possibility to force the algorithm to see all examples of the two different classes, even though they are not equally distributed, is to use the smoothing. The smoothing is one of these techniques we have seen before, the equal size sampling. The equal size sampling is an undersampling technique that reduces the two classes to have the same number of patterns by subsampling, undersampling the majority class. The smooth is the opposite, so that's the opposite. It takes the two classes and it oversamples the minority class as to have the same number of samples as the majority class. So it creates synthetic artificial data with the same statistics properties for the minority class in a way that then at the end I have the two, I have samples, I have the same number of samples for the two classes. So this is another one of these techniques. Again, this is the training workflow. We would have a deployment workflow like the one before. The deployment workflow takes the model, takes the new data, applies the model to the new data, and then performs some kind of a prediction. In this case, it performs the prediction into the risk class. For example, when let's say you are in the call center, you are the agent, all the customers have been scored, and then when you pull out the data of your customer, then there is going to be a field which is called credit risk, and is going to be assigned to a specific risk class. In this case would be high. And then based on the strategy of the company, the behavior of the call center agent will be different depending on the credit risk class. Anyway, so those are just some of these different, just some of these customer intelligence and finance examples. Recently, we have put together with a professor from the Luis University in Italy, we have put together a bucket on the KNIME Hub. You remember the KNIME Hub is this repository where people can put their own workflow and share it with the community. So we put together a bucket on the KNIME Hub, and if you want to access it, here there are some marketing analytics examples, including the churn prediction, the search engine optimization. There is going to be some sentiment analysis, of which I'm going to talk later, the customer experience, topic modeling. So there are some of these examples. I only show the churn prediction and the risk assessment. But you can use some more. You can download them and then customize them based on your data and your needs. Okay, any questions on that? Otherwise, I'll start with the IoT. I can send you the slides afterwards.
Or maybe we will have a Q&A session towards the end of your presentation. So maybe they can give their questions, type the questions in for later as well. So you can just maybe continue. Yeah. There is a question about the rough sets. So KNIME has the some of the fuzzy sets algorithm. I don't think we have the rough sets, but they could be taken from Weka or from R or from Python. That's why these extensions make it so powerful. Okay, let's talk about the IoT. So the IoT, the biggest problem that I always face when I work on IoT problems, because when the machine learning is actually easy. I know it sounds trivial what I say, but the machine learning, it's easy. Once you have the data, you split training set, test set, train the model. So I mean, it's one node or one instruction if you use Python. So it's the easy part. The most complicated part is actually to collect the data from weird data sources and, you know, strange and new, and then you have to do complicated things to be able to access the data sources, for example, like the sensors in the IoT.
And that's where KNIME actually helps a lot, because we have a lot of connectors for many different data sources. I told you that we wrote a whole book about that. It's the Will They Blend collection of blog posts. So this is actually the part where KNIME makes life much easier. So let's talk about weather forecasting. We have a bunch of weather signals. We have a board that we bought, and I put it outside of my window. And then we want to collect the weather signals to be able at some point to make some prediction from today's weather or the past day's weather into, for example, the maximum and minimum temperature for tomorrow, so that I know that tomorrow it's going to be cold or it's going to be rainy, so I know how I can dress up to come to work. The first step, whatever the next machine learning algorithm is, the first step in any case is to collect the data, which means I want to install a board that collects all this, that samples the humidity, pressure, and temperature, and then I want to transfer all this data into a data repository, for example, a Snowflake data repository, for example. Okay. So let's see how we did it. We bought an Arduino MKR IoT carrier. We set it up. It was a bit complicated, but we set it up. We finally put it outside of the window. And this Arduino board is sampling temperature and humidity and pressure I think it's every half an hour. We set it to sample it every half an hour, I think. You can set different sampling frequency depending on how high you want the resolution to be. Okay, so this is the board. We, of course, expanded the board using a Wi-Fi module because we want to be able to access the board through our Wi-Fi, and then implement a web service that collects the data from the Arduino board and writes them into the data repository, okay, into the Snowflake database. So let's concentrate on this web service. That's what the web service, that's what the whole data collection is. The Arduino, every time the Arduino board gets a new sampling of the data, is going to call this web service and is going to send a request, including this new measurement. The web service is going to write this new measurement onto the Snowflake database, and then also onto a Google Sheet just for backup reasons. And then it's going to send back a message of success or failure of writing into the Snowflake, receiving the data, writing into the Snowflake, and writing into the Google Sheet. Yeah, that's all this web service is doing. And this is the code that is running on the Arduino board, and is the code that is calling and sending the data to the web service, and the web service is residing on the KNIME server. And that's the workflow that I use to implement my web service. The request is in JSON format, and the response of the web service is also in JSON format. To accept JSON formatted request objects, I use this container input JSON node, and to produce the JSON formatted response, I use this container output JSON node. Now, every workflow that I create with KNIME, if I put it on the KNIME server, it's available as a web service, all of them, right? All of them. The only difference that I can make is that my web service on the KNIME server has to be able to accept requests and has to be able to produce response objects. To allow my workflow to accept the requests, I use this node here, this container input, in this case in JSON format. There are other formats available. And I use this other node to produce my response. So this is the only customization to a workflow to make it available as a web service that receives requests and produces responses. Okay, so I receive the request in JSON format. It contains humidity, temperature, and pressure. Then I transform this JSON format into tabular data, the classic tabular data that KNIME accepts. I create a timestamp because, of course, I want to know when this recording has been made. I join everything together, and then here I have a node that a component, not a node, a component that performs my database update on Snowflake, and then another component that performs my Google Sheet update with the new measurements. Finally, if everything goes well here, then we proceed here. If everything goes well in the Google Sheet writing, then we proceed. If we proceed, we are going to have the original input data plus the status of the writing on Snowflake and the status of the writing on Google Sheet. We move everything into JSON format, and then finally we produce the response using the container output JSON node. It's a relatively easy workflow. It's really not that complicated. At the end, it's only a few nodes, mainly due to the JSON transformation, and then the writing into the database and in the Google Sheet. Let's see what's inside this component. As I said, a component is a node with inside other node. So this component contains the credentials, contains the Snowflake connector, and contains the node for the insertion of the new data at the input of the component into the Snowflake database. Now notice that, of course, we want to, a lot of things can go wrong when you write stuff in a database. For example, in this case, I didn't have I was not allowed to write onto this database. My credentials, the ones that I had, were not allowed to write in this particular table of the database. So in this case, to ensure that there is a graceful exit of whatever problem you had, we have this try catch nodes that if everything goes well, they follow the upper branch and everything is successful. If something goes wrong in the upper branch, then they fall onto the lower branch, and usually the lower branch contains a message or a code that indicates the failure in this particular task. Also here, this second part, sorry. This second part allows to log for logging of the operation in a log file. So this is what I do. And the component for the update Google Sheets is similar, only that instead of having the credentials, we have the Google authentication, and then we have all the nodes that allow you to access the Google Sheets and write into them. Again, we are going to have a try catch construct so that the upper branch is for the successful writing and the lower branch is for alternative error codes when something goes wrong in the upper branch. So it's relatively easy, and I don't have to do complicated things to access the data that are sent by the Arduino board. Okay, so let's move now on to the weather forecasting. The weather forecasting, now in this case, we have the weather signals, we have collected them, we have a model, and we want to be able to predict tomorrow's weather based on the previous day's weather. This is also relatively easy. We connect to the Snowflake database. You remember, we wrote all the data into the Snowflake database. We do some selection and some data extraction from the Snowflake database. We convert since the date and time is extracted from the Snowflake database as a string, so we convert it into a date and time object. And then we start with a number of components that are available in the time series extension. So we perform the aggregation granularity just to make sure that every half an hour or every hour we have a number that describes the average temperature for that hour, or the average pressure, or the average humidity. We perform an alignment, so if there are missing measurements, we substitute, we still have a field, a row for these missing measurements, and it's going to be a missing value. We perform the missing value imputation, if any, and then after that, we are going to partition again for the top, again for the top part, we are going to have the training set, and for the lower part, we are going to have the test set. We are going to train a SARIMA model. A SARIMA model is a time series model. So the SARIMA model, based on the previous 24 hours, is going to tell you what the temperature is going to be in the next 24 hours. And then we apply the predictor, and then we perform some forecasting of the we perform a forecasting for the next 24 hours. Okay, so let's so this is the training, that's a trained model, and then we are going to use this model to actually perform the real forecasting for the next day. So in this case, we are going to again read the model, the SHRDC model that we have trained before. We apply the new data. So we start with the latest data, and then we start with the new predictions over the next 24 hours. And that's where we use the SHRDC predictor. After that, we are going to separate between the training set and the test set. So the data that, so the real data, sorry, the real data and the predicted data, and then we are going to visualize the data using a dashboard. And this is the prediction. So this first part is the data used for the training set. Of course, in this case, we are talking about time series. So when we talk about time series and we perform a partitioning and we say that we use the 70%, 75% of the data for training set and 25% of the data for test set, of course, the time order must be preserved. For the decision tree that we have seen before, or the random forest that we have seen before for the churn prediction problem and the risk assessment problem, in this case, the extraction of the training set and the test set was random. But for the time series, that cannot be, because we have to preserve the time order of the data. So in this case, we use this, the 75%, we take it from the top, which is the past, and then the remaining 25% to evaluate the model on the test set, we use it from the bottom of the data, which means into the future, so into the latest time segment. So again, this is the training set, and then starting here, we start with the predictions, and then you can see that the predictions is maybe not perfect, but close enough to the real value. The yellow ones are the real values, the blue ones are the prediction. And here you can see the scoring matrix. So we are going to have an R square of 0.22, the mean absolute error, and those are all classic errors used in evaluating prediction of time series. Okay, so I predict my the weather in my next 24 hours, in this case actually 48 hours, and then I extract the maximum and minimum temperatures for tomorrow. And that's the, I'm going to show these maximum and minimum temperatures in a dashboard for me to understand how I have to dress up tomorrow when I go to the office. So this is a signal forecasting. We use the weather forecasting, but of course, can be applied to any kind of other signals. Another classic problem in time series analysis, the demand prediction. And here we are going to talk about the energy prediction, the energy demand prediction. So in this case, again, I have an energy demand in the past. It's not a signal that comes from a sensor. It's just a signal that comes from usage in the past. So here we have, this is an energy consumption by a cluster of users, I think in Ireland. And you can see here there is a 24 hours seasonality. You can see the peak around 1 o'clock. And then you can see also weekly seasonality. So Monday, Tuesday, Wednesday, Thursday, Friday, and then these two small ones are Saturday and Sunday. So this is like the business. Those are businesses, and you can see that they have a 9 to 5 seasonality peak, and then they have a Monday to Friday activity. Okay, so this is a relatively nice data set, nice seasonality, relatively clean, so perfect. But my question is, I have the energy demand in the past. I want to know what the energy demand in the future is. So today is Monday. I want to know if on Wednesday at noon, how much kilowatt I need on Wednesday at noon. Of course, predictions, before I showed you the weather forecast based on the previous 24 hours. Of course, the quality of the prediction depends by many things. It depends by the model, depends by the parameters of the model, and it depends, of course, also on the length of the past used for the prediction. So if I use the past 10 hours, then I'm going to have some quality of the prediction. If I use the past 100 hours, then I'm going to have another quality of the prediction. If I use the past 200 hours, I'm going to have an even better quality for the prediction. So this is also, there are many parameters to play with in this kind of models. As you see here, with 10 hours, the prediction was, let's say, not fantastic. But then if we already move over the 100 hours, the predictions starts very well, it degrades, but it degrades, slowly degrades the farther we go into the future. If we use a past of 200 hours, then the prediction remains reliable for many days. So 1 week, 2 weeks, I can easily predict reliably 2 weeks of demand into the future. So let's see how we performed this prediction. Again, we read the data, we perform some transformation on the data, we use the components from the time series extension for the timestamp alignment, and then we decompose the signal to make sure that we get rid of the seasonality. I told you there were 2 seasonality in this signal, weekly and daily seasonality, and then again we partition the data. 75% from the past is used to train the model. The next 25% is used to test the model. And then here I have I train my SHRDC model. I perform a prediction into the future, and then I evaluate the quality of my prediction with respect to the real values. Okay, so this is exactly the same as the weather forecasting. The only difference is that the data is not coming from a sensor. So this is the classic modeling. So it's the classic SHRDC, ARIMA-based modeling, the classic statistics-based modeling. Lately, the deep learning has been used for time series prediction. That's because, for example, the recurrent neural networks, and inside the recurrent neural networks, the long short-term memories, they have the capability of remembering the past. So they have this long short-term memory layer, which, using the recurrency of the output back into the input, is able to preserve some remembering of the past. Remembering of the past, of course, comes useful when we talk about time series analysis, like in this case, the demand prediction, but also the weather forecasting from before. Talking about deep learning, KNIME has an integration with the deep learning framework from Keras in Python. So you are going to create by drag and drop all these nodes, and these nodes graphically expose the parameters of the long short-term memory or other deep learning networks without you having to write any code. So in this case, we have an input layer, then we have an LSTM layer, and then we have an output layer. It's a very, very simple network. I can still perform the same data transformation as I did for the SHRDC learner. But in this case, instead of applying a SHRDC learner, I'm going to apply a Keras network learner, which trains the network that I have defined here. Again, after that, I'm going to evaluate how well my model is performing the prediction. And now, and then if both models are acceptable, either the SHRDC or the long short-term memory, I am supposed to build a deployment workflow, which is the one that is going to generate the data into the future until I reach my Wednesday at 12, and I know more or less how much kilowatt are needed for Wednesday at 12. So let's have we tried the SHRDC and we tried the long short-term memory. The long short-term memories work better than the SHRDC model, also because the long short-term memories are more flexible to configure. You can use many more parameters. Of course, the flexibility we pay with a much heavier load when training the model. I mean, if the data set is big, the long short-term memory can take a long time. So using the 200 past hours of demand of energy, we were able to correctly predict the first demand of energy for the next 5 days, and then of course also for the other days. But then the farther I go into the future, the more the performance degrades. And then we know that on Wednesday at 12, we need the 16 kilowatt for that particular user group of energy consumers. Okay, let's continue. So when we talk about IoT, we always talk also about anomaly detection. Anomaly detection is the problem of being able to recognize when a machine is degrading, is somehow close to break up before it actually breaks. These machines are quite expensive. In this case, we were talking about a rotor. These machines are quite expensive. They cost millions of euros. So we don't want them to we don't want to retire them from functioning too early because we paid a lot of money for them. But on the other side, a lot of other smaller machines depend on them. If they break, the whole chain breaks. So we don't want them to break. So we want to use them as much as possible, as long as possible, without them breaking. And this is the complicated part. So now there is a fixed time. After this fixed time of service, they get substituted, changed, repaired. But then it would be nice if our time series forecasting was able to recognize when the machine is going to break, and we just use it as much as possible. So in this case, we had this rotor. You can see that the machine was working nicely. Then it started to become unstable until it broke on July 22nd. The July 22nd, it was substituted, and that's the working of the new machine, right? So what we want to do, we want to train our model on this window, then have an observation window for maintenance. And then if something like that happens, we want to be able to stop, change the machine before it actually breaks. Okay. The problem of this kind of anomaly detection tasks is that since this equipment costs a lot of money, I know how, so I have a lot of examples of data coming from sensors monitoring machines that work in normal conditions, that work well, but I don't have many examples of data coming from sensors monitoring machines that break, because they never allow them to break. So how am I supposed to train a supervised machine learning if I have only examples of correctly working machines? So, well, we have to do with what we have. So we are going to train a model on only normal values. And then we are going to train it on this training set. So the machine here is working correctly. And we are going to train the model to predict the next sample based on the previous n samples, right? So, and then after that, we are going to apply the model for the future, and we are going to predict. So the model was trained to predict the next sample based on the previous n samples. So we are going to use the model like that. We apply the model using the past n samples, and we predict the next samples. Now, as I said, in the training set, I only have examples. I only have measures of describing a machine working well, a machine working in normal conditions. So if I calculate the difference of what I have predicted, so I have a training set describing only a machine working well. So I train my model only to predict measurements of a machine working well. So during this predictive maintenance window, I am going to use the model to predict the next sample, and then I'm going to measure the difference between what I predicted and what the real value of the measurement is. If the machine is working in normal conditions, the difference is not going to be that big, because I predicted that the machine would be working in normal conditions. The machine is actually working in normal conditions, so there is going to be some random difference, but it's going to be a small value. On the opposite, if the machine starts to degrade, the difference between the value that I predicted and the value that the real value is going to be bigger and bigger the more the machine is degrading. So I can define an alarm system so that if this difference in the predicted value and the real value becomes bigger and bigger for longer periods of time, then in this case, I'm going to fire an alarm. The alarm doesn't mean that the machine is breaking, but it means that it requires attention because something is not correct anymore, since the prediction of the value for a machine working in normal conditions doesn't apply anymore. And this is what we did. We did that across different frequency bands and across the different sensors. We had 28 sensors and many different frequency bands coming out of the sensors. So summing up all those predictions, we had 300 models. Each model was predicting for each sensor, for each frequency band, was predicting the next sample for a rotor working in normal conditions. So summing up all of them together, you can see that nothing happens for a long time. The difference between the real values and the predicted values is tiny, but then on March 6th, something starts changing. Okay, maybe not enough. So okay, let's be tolerant and let's wait until we arrive in May and we see that the model has been degrading a lot. So this is the first the first sign that cannot be ignored. So here there must have been some maintenance until, so between May and July, then at the end, in July, the rotor will break. So we had plenty of time to examine, to repair whatever was wrong with the machine. Okay, so this is one of these examples, the anomaly detection. Whatever is connected to so in the deployment workflow, we are going to pass this threshold. The threshold is going to generate an alarm. Whatever the alarm is, if it's an email to the mechanic, if it's a shutdown of the system, if it's a call for an emergency procedure or something, of course, depends on the business. A nuclear plant is different from, I don't know, a pasta making machine, right? So in this case, depends on the business and depends on the company. Okay, a similar problem is also in cybersecurity. In cybersecurity, when we are dealing with credit card, when we are dealing with credit cards fraud, in this case as well, we have a data set that has a lot of normal legitimate transactions, and then we have a few transactions that are that have been labeled as fraud, but they are not that many. A bit because we don't recognize them, and a bit because they actually are not. For good luck, they are not that frequent. So how are we supposed to train a supervised machine learning model without examples for the fraud class? Because it's really not that many. There are only a few. So in this case, we have the transactions from the credit card on one side. We have our model, and then we have all legitimate transaction, legitimate transaction, legitimate transaction. And from time to time, we have a fraud transaction, or at least maybe not fraud, but a suspicious transaction that we want to identify. And we have no examples for those. It's the exact same problem that we had for the anomaly detection in the mechanical plant. So if we had enough examples, we would use the usual workflow, right? We partition, we train a model, we apply the model, and so on. But we don't have enough examples. So one strategy to apply when we don't have enough examples for credit card fraud detection is to use the autoencoder. The autoencoder it has a similar philosophy to what we used for the anomaly detection prediction. The autoencoder is a neural network, is a classic neural network with trained with backpropagation, fully connected, feed forward, so no recurrence, nothing fancy, just classic neural network. The only particularity of this network is that it has as many input units as many output units. So what I train this network to do is that on the training set, I'm going to train the network to reproduce the input vector onto the output layer, right? That's all what the network does, learn. And I'm going to do that only for the legitimate credit card transactions, because that's what I have. So in this case, then during the training set, the network is going to learn to reproduce the credit card transaction, the legitimate credit card transaction from the input layer onto the output layer. Again, so this is how I train the network. When I apply the network into deployment, I am going to, again, give as input a credit card transaction. The network is trained to reproduce legitimate credit card transactions onto the output layer. So if the credit card transaction is legitimate, then shouldn't have a problem in reproducing that on the output layer. But if the credit card transaction is a fraud or strange or something is suspicious, then the network is not going to do a great job in reproducing this input vector onto the output layer. Yeah, because it hasn't been trained to do that. It has been trained only on legitimate transactions. So if I calculate the distance between the input layer and the output layer, then this distance is going to be very small in case of legitimate transactions, because the network has been trained to do that and knows how to do that well. And it's going to be much bigger in case of fraud or suspicious transactions, because they were not part of the training set and the network has not been trained on reproducing them on the output layer. So the philosophy is similar. I train a model onto a training set made of only normal examples. The model predicts the next normal examples, or reproduces the normal example onto the output layer, and then I calculate the distance between what the reality is and what has been produced by the model. And if the distance is too high, then I fire an alarm. Doesn't mean that the alarm is a fraud or the machine is going to break, but it means that there is something that requires attention. This is the workflow that I use to implement the autoencoder. That it's a bit complicated because some of these nodes, they perform just a normalization of the previous layer. And it was a bit, this is a 3-layer network. We actually used a 5-layer network, but the structure is the same. Input, same number as unit on the output layer. And then there is one additional layer in between in the output part and one additional layer in the input part. So it's a bit more complicated than what I showed there. Those are the Keras layers. So I create this network based on the Keras libraries in Python. Then I read my data, I perform some transformation on the data, and then finally I train this network onto the data set made by legitimate transactions. I apply the autoencoder to the test set data, again made of legitimate transaction, and then I can measure how good my autoencoder has been trained to reproduce legitimate transactions on the output layer. And then during deployment, and that's the interesting part, is where I apply the model, so my network. I put it, this is my network here. I read the new data, and then based on how my network reproduces the transaction onto the output layer, I calculate this distance between output and input, and then I fire an alarm. The alarm is defined here in this rule engine. I fire an alarm if the distance is too high. Okay, and then at the end, what I get is that transaction legitimate, 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 suspicious transaction. And then in this case, yeah, depends a bit on the policy of the credit card company. There is either an SMS to answer or a telephone call, or something happens between the bank and the customers. This kind of approach generates a lot of false positives, because of course we are basically poking in the dark to find suspicious transactions or to find suspicious malfunctioning in the machine. However, depends a bit on the cost of the false positives. In the case of the credit card transactions, a cost of a false positive is an SMS to answer. It's not that much. So we can tolerate, based on the cost of the false positives, we can tolerate a high number of false positives. Of course, there are businesses where the false positives are absolutely not tolerable. For example, in medicine, if the false positive means that somebody is going to die, then of course this kind of approach cannot be used. But in some cases, like the fraud detection or the mechanical inspection, the price to pay is not that high, and we can tolerate a higher number of false positive if the counterpart is much more expensive. Okay, I have the whole part of social media analysis, but I think I don't know if you want, I can tell you some more, but I don't have a lot of time left, so maybe I can show you quickly how to build a sentiment analysis and how to build a word cloud. So let me see now the question. KNIME can communicate with Node-RED. I don't know Node-RED, probably. So Node-RED is a database, I assume. And I mean, if there is a database node, is the generic database a connector, and the generic database connector needs a JDBC driver, and then based on the JDBC driver can connect to any database. There is no specific node for Node-RED as far as I know, or another way is to connect via web service. If the Node-RED has a web service connection available, then we can connect via web service. What is the independent variable X used to predict energy demand? For the energy demand, we use the past values of energy demand to predict the next energy demand. So this means we had these 10 hours. So every hour we had the energy demand for that hour. So we use the past 10 hours to predict the next hours, the demand in the next hours, or we use the demand in the past 100 hours to predict the energy demand in the next hours, or we use the past 200 the energy demand in the past 200 hours to predict the energy demand in the future. Of course, the more past we use, the more accurate the prediction is, of course. KNIME can communicate through MQTT. I don't know, I have to ask this for this question. Yeah, I'm going to ask for this answer and then I will let you know. Okay, so for social media analysis, the last 10 minutes, we can build a word cloud. That's the easiest one. Here there is an example of building a word cloud from Twitter. We have a bunch of connectors to connect to Twitter, but also to connect to Google Analytics, to connect to a number of these social media channels. The Twitter is the easiest one because Twitter doesn't require for permission. So it's just open, right? I can collect the tweets from everybody and I don't need to ask for permission to whoever sent the tweet. Connecting to Facebook and to LinkedIn, of course, is much more complicated because of this permission, privacy protection. Anyway, so I connect to Twitter. I use the Twitter API connector. I need a Twitter developer account, but then once I have it, I can connect to it using the Twitter API connector. And then I have a number of nodes that perform the search or the posting or the user description and stuff like that from Twitter. I use a lot of the Twitter search because I want to know what people say about KNIME on Twitter. So in this case, for example, this is an example. We wanted to download all the tweets that included the hashtag COVID-19 Europe that was last year. As you see, the workflow is quite simple. Connect to Twitter, Twitter search for this hashtag here, COVID-19 Europe. Then there is some shaping because we want to provide the word cloud. And then in this component, we have a node which is called the tech cloud, and that's the node that builds the word cloud. So the Twitter search, this is the configuration window. This is the query based on the hashtag COVID Europe or COVID-19 Europe or coronavirus or a number of other COVID synonyms. And this is what I get out of the Twitter search. So you can see here there is the username, the picture, the icon of the user, and then the full tweet, the ID, and then a number of the time and a number of other information about the Twitter user and the tweet themselves. This is the pre-process, so that means a lot of conversions from the text string to the document. The document is a bit of a more sophisticated structure with respect to the simple string and to the date and time. Okay, but this is not so important. And then after that, we build this interactive view by combining this table, this legend, and this word cloud. So we use the tech cloud node to build this word cloud, and then we use a table view to build also these other tables. That's the nice thing about components. If you put inside a components nodes that have a view, then all these views get combined in a composite view like this one, which where all the views interact with each other. For example, now I'll start it. For example, here I can select one word in the word cloud, and then of course the table gets populated accordingly to the word that I've selected. So for example, here I have a COVID-19 Europe, and then I get here all the tweets that contain the COVID-19 Europe and have been tweeted in the afternoon, evening, morning, or night. This is a very relatively simple workflow. Another thing that I want to show you is that the sentiment analysis of social media activity. You know what sentiment analysis is? There are a bunch of reviews. Some are positive, some are negative. So in this case, for example, this is well exceeded my expectations, of course, is positive. Very bad experience, of course, is negative. Now, those are too easy reviews. Sometimes people, they write long reviews and it's hard to understand what if it's really negative or positive. There are negations, there are grammar constructions that are not that easy to immediately translate into positive or negative. There are two different approaches in this to spot the sentiment, to measure the sentiment. One is the lexicon based, which means they use positive words that are identified as positive and negative, and they use the grammar constructions to identify how these positive and negative words get combined together to produce the final meaning of the sentence. This is a lot of linguistic expertise. And then the other approach is machine learning, and then recently as a spin-off of the machine learning, deep learning based solutions. In this case, we go by a supervised learning technique. So in this case, we have a data set with reviews. Each review has been labeled as positive or negative without any grammar knowledge. So by a human has decided this is positive, this is negative. And then all these review texts are fed into a supervised machine learning algorithm. And then the algorithm learns that these words in this sequence produce this kind of sentiment. And this is what the model has been trained to. Now, the grammar knowledge is ignored here when we use the machine learning approach. So it can be very primitive because, for example, if I say I like these shoes, that's a positive statement. But if I say I don't like these shoes, like is still a positive word, but don't, the negation changes the polarity of the sentence. So this is hard to find if we don't take into account that like is preceded by don't, and which means if we don't take into account the sequence of words, the context. As you remember, we have used deep learning for demand prediction. Deep learning is, especially some of the recurrent neural networks are able to keep into account they have some memory, so they keep into account the past history of the input signal. So we could use the deep learning to remember the context of the previous words in the review. So in this case, if I say I don't like these shoes, when I reach like, which is a positive word, I remember that before there was a don't, and then like is not positive anymore because there is a negation. Those are the solutions, as I'm going to be fast. So those are the solutions. This is based on grammar rules. So we have a list of positive words. We have a list of negative words. They are coming from linguists. And then we assign a +1 for all the positive words, a -1 for all the negative words. We define some grammar rules if we want to be very sophisticated, which I'm not because I'm not a linguist. And then we count. We count how many words are positive, how many words are negative, how many words were positive and then they became negative. We do the full sum, and then based on the full score of the sentence, we can say if this sentence is negative or positive. The second approach is the machine learning. So here we read the data, we have a labeled data set. That means we have a training set with labeled reviews as positive or negative. And then we perform some pre-processing dedicated to text. And then again, we partition the sentences into some sentences are going to be used to train the model and some sentences are going to be used to evaluate the model, like all the other machine learning based prediction approaches. And then the last one would be on deep learning. In this case, we use again long short-term memories. As I said, those are the ones that have some memories of the past. So we build a network which has an input layer, an embedding layer. The embedding layer is used to encode the text. The text, and I'm not going to describe that here, but the text encoding is a huge topic because each word has to be translated into a number. How do I do that? And different encoding strategies have different drawbacks and advantages. So anyway, I'm not going to discuss that here, but anyway, the embedding layer here is used instead of the encoding. We apply then the long short-term memory, and the last one is the output layer, which is going to produce the probability of a sentiment being negative or positive. Here I read the data, I perform some realignment of all the sentences because the reviews, of course, have different length. Some people write a lot, some people don't write anything. So we perform some zero padding and truncation of the original reviews, and then we train the network, this network here, based on the reviews that I've used for the training set. And then we apply the network to evaluate, to the test set to evaluate its performance. Okay, so this is the approach based on deep learning. Yeah, so I think I'm going to skip some of the other examples. As you see, I have a lot of different examples. And I'm going to conclude with this thank you slide to thank you to have remained with me until the end of this presentation. There is a free book, a free copy of the ebook Practice in Data Science. This Practice in Data Science contains a full collection of case studies. Most of some of the ones I've described to you today are included in the Practice in Data Science. So just use this code here and download it for free. That's it. Thank you for listening to me. Are there any questions?
Rosaria, for your talk. So since we're running out of time actually, so we will wrap this up shortly. But before that, we will address any questions from the participants from the floor. If you have any for Dr. Rosaria. So
there is one question, if it displays the data in real time. What does it mean? If you collect the data in real time, sure, you can display the data in real time.
Oh, Dr. Rosaria, I think he meant this person, maybe they are meaning streaming, right? Real-time streaming of data into KNIME.
So we have a Kafka node to collect the data in real time. You can, I mean, I get this question a lot. What does it mean real time? You can have a web service that gets pinged every second. So it depends a bit what real time for you is. If you want really the microseconds, nanosecond real time sampling, then sure, we have some Kafka nodes that can do that. But usually, I don't know, I have to say rarely they need such a high frequency of the sampling signal.
Okay, thank you, Doctor. Do we have any more questions from the floor? Any queries, concerns from anyone attending? Do type your questions away. Okay, so we do have a raised hand from Mr. Rusli. Do you have a question for Dr. Rosaria? Rusli? Okay.
If there are no questions, I think we can conclude here.
All right. So before we move on with Dr. Chua with his sharing session for the last bit, do you have anything that you want to wrap up, Dr. Rosaria? Any last thing that you want to wrap up? Yeah.
So this is the final slide. If you want to read more about these case studies, please download the book. I'm going to share the slides. I'm going to send it at the end of this webinar. Yeah. Start the 66 days of data challenge if you want to learn more about how to do data visualization with KNIME. Yeah.
All right, then. Thank you very much, Dr. Rosaria. So, okay, Dr. Chua, maybe you can take over the session for now, for the last part.
Sure, no problem. Thank you very much, Dr. Rosaria, and thank you very much, everybody, for staying on until the last final sessions. I'll just do a quick sharing, right, on a little bit about what SHRDC is doing. And KNIME is actually one of our very, very good technology partners under the Malaysian Smart Factory. And in fact, under the Malaysian Smart Factory, this is actually a center located in Shah Alam, if you have not been here before, right? Currently, we are not open yet, but we do invite you to visit the virtual tour. And of course, if you would like to have a discussion with us on anything related to Smart Factory and Industry 4.0, next week, we actually have a session that Marisa will actually send out an email on Ask Me Anything session next week, right? Actually, that's in line with our 3rd year anniversary, right? The Malaysian Smart Factory is 3 this year, right? So that's on the 25th of September, right? So we are going to have a session and we are opening up for all, and you can always come and see our virtual tour. We run multiple programs from level 1 to level 5. Just now, Dr. Rosaria has shared KNIME, right? The KNIME platform, that's actually part of the data analytics, right? And of course, now there's also extension to deep learning, which is also something that we are working with on KNIME to actually introduce it to the community in Malaysia, right? So we run multiple programs that cover from level 1 to level 5, right? So these programs are then divided into levels of, modular kind of programs that we deliver, right? So we also run a data analytics program using the KNIME Analytics platform, right? So if you are keen and interested to explore, you can always come and meet us. We also run multiple other system integration programs. And of course, we are running some ongoing promotions, right, with our programs. If you are really, really keen and interested to explore, and if you're ready to embark on a journey with KNIME, for example, please do let us know, and we are more than happy to support you on this journey, right? So with that, do keep in touch with us. A lot of our webinars are run very, very frequently. Throughout the session, we have one running next week and then the following weeks in October. So do keep in touch, right? And these are some of the resources that you can, of course, explore with SHRDC, and we are more than happy to support you through on your journey towards digital transformation, right? So with that, I believe that's all I have to share, Marisa. Just a quick and short one, right? Thank you. Thank you very much.
Thank you very much, Dr. Chua, for that. All right, so since we're about to end the session now, I will just share a quick poll for your feedback. I'm just going to launch it, just a simple 3 questions. Appreciate your feedback. All right, so do answer them. All right, meanwhile, I believe I had missed out on the part where I should have been introducing Dr. Rosaria during the introduction. So I will just quickly run over the slides, which I had missed earlier on. Okay, so for those who are here, I would just like to let you know that you guys will be receiving a webinar e-badge. It's something like an e-certificate, okay, for attending today's webinar. And aside from that, okay, I believe during the poll questions from Dr. Rosaria earlier on, that many chose the answer that you guys have not heard of KNIME before this. So let me just do a very quick and brief introduction. All right, so Dr. Rosaria Silipo is once again, she is a principal data scientist at KNIME. Okay, so you can see here, this is a very brief introduction or background on Dr. Rosaria. So you guys can see that She has spent the last 25 years in applied AI, predictive analytics, all right, and machine learning, basically surrounding data science. So she has a very vast background and expertise on this. Okay, so and you guys can also see that she has authored more than 50 technical publications. Okay, this is part of her books. You guys can see here, and aside from that, her expertise also include in data science tools and management skills. All right, so this is the introduction part for Dr. Rosaria that I should have let the audience know. Okay, so apart from that, so this is SHRDC contact in case any of you guys would like to get in touch with us, talk to us about anything surrounding data science, any of our training programs or courses. Feel free to reach out to us via any of the socials. All right, and from SHRDC behalf, from me, okay, I would like to thank everyone, especially Dr. Rosaria, for joining us and for giving the wonderful insights on the Codeless data analytics. All right, thank you very much. So,
Thank you.
Is there anything else? So, is there anything else that you guys want to say or wrap up, Dr. Chua or Dr. Rosaria?
On my side, thank you very much, everybody, for joining the session today. I hope it was very, very beneficial for all of you. And, that Dr. Rosaria has shared very, very interesting use cases and examples for analytics and, the power of KNIME, like what it can do for you in terms of codeless analytics. So do kickstart your journey towards that. And she has also provided a good promotional code for a book, and you can, download it and have a look at some of the use cases, and hope that we can support you through on this journey. Thank you.
Thank you, everyone.
Thank you, Dr. Rosaria. Thank you very much
Thank
for your
you.
time.
Thank you.
So how was it, everyone? Did you enjoy and learn something new today? We hope you find the webinar beneficial and informative. Thank you for sitting through until the end of the webinar session with us. If you like what you have experienced today and want to join in for more sessions, do not forget to like and follow our social media channels. Simply search SHRDC on Facebook, LinkedIn, Instagram, and Twitter, as all of our programs are regularly updated there. We will include the links to these pages in the description box below. Feel free to connect with us today or visit our website at www.shdc.org.my. Thank you, and we hope to see you again.